this R tutorial video, we'll learn how to run a simple linear regression, which is a regression model with just a single independent variable. And for this video, I'm going to use the medical data dataset. I'm just going to import it and call it med. And this dataset contains various measurements from patients at a doctor's office. And the two variables we're interested in here are BMI and blood pressure. Let's say we want to investigate the contributing factors to high blood pressure. And to start, we want to see if BMI is linearly related or a significant linear predictor of blood pressure. So let's just make a scatter plot of these two variables. I'm going to plot the independent variable BMI first, then the dependent variable, and then I'm going to give it an appropriate title and axis labels. Remember to include units. And also I'm going to change my PCH to 20 so that the points are just filled in dark circles and they look a little nicer than the default. So here's our scatter plot. We can see a slight upward trend. As we increase BMI, we are going to be increasing blood pressure, but they're not strongly linearly related, at least it looks like in the scatter plot. However, because there's no clear nonlinear trend, we would say that we pass that assumption of linearity. Now to check the other assumptions, we're actually going to have to build our model first. So I'm going to create a model object called myModel and use the LM function. So the linear model function takes the dependent variable first, which is blood pressure, then a tilde sign, and then any independent variables. So if we run that, we're going to be assigning this linear model object to the name myModel. And from this object, we can pull out the residuals of our regression model, which are what we need to check for the next two assumptions. First, we want to make sure that the residuals are approximately normally distributed. So we can make a histogram or a QQ plot, which is what I'm going to make. And we can actually go into the myModel object and pull out the residuals by just saying $residuals. So residuals is a vector that is contained within any linear model object. And then I, of course, will make the QQ line on my graph. And I'll color it red just so it stands out. And we can see a very normal distribution here in our QQ plot. So we definitely pass that assumption of normality. Now, in addition, we're also going to want to look at a residual plot, which we can confirm the assumption of equal variance with. So I'm going to make a scatter plot again, but this time I'm going to call myModel fitted values to be on the x-axis, and these are actually the y-hats, or the predicted values based on our model. And I'm going to plot those against the residuals. And because most of the time we want to see a nice line at 0, I'm going to add an AB line, h equals 0. And that will give me a horizontal line at the intercept of 0. And again, I'll color it red just so it stands out. And what we can see with our residual plot is a nice, fairly random scatter both above and below the line. There's no funneling, so we don't have a violation of equal variance. So we are good to go on the assumptions of regression. Now we can ask R to give us the output of our model by using this summary function. And we just have to pass it our model object. So when we run that, our console now shows us the summary of our regression. In this coefficients table, we have the intercept and slope estimates. So we would interpret this intercept estimate, 49.24, to be the average blood pressure for a patient with a BMI of 0. Probably doesn't make sense in the context of the problem, but that's what the intercept means. Now our slope estimate for our BMI independent variable is 0.67. And that means for every average increase of 1 BMI unit, we would expect the blood pressure to rise about 0.67 units. And we see our t-statistic and p-value here indicating that it is a significant predictor of blood pressure. One more thing our output tells us is this r-squared, which is 0.18. And so even though we are accounting for a significant amount of variation in blood pressure, we're only really explaining about 18% of it based on the variation in BMI. So one final step we might want to take is to go back to our original scatter plot of our data and overlay the line of best fit on it so we can actually visualize that linear regression model. And I can again use the AB line function for this. Instead of giving it an h equals 0 for her horizontal line, I can just give it my model and it will actually plot that fitted line onto my graph. Again, I'll make it stand out by making it red. And here we see our data along with our regression model.